Welcome everybody on Zoom, welcome everybody in the lecture hall, welcome everybody from the future. Today on the menu we have the continuation and hopefully the end of the lecture on querying denormalized data, which by now you know is trees. If time permits, I might start showing you another data shape, graphs, but for now let's begin with two questions that I have for you. So here's the first one. Which of the following adjectives qualify a well-designed query language? So you have four propositions: functional, imperative, low-level, and declarative. Multiple answers possible. This is specifically about query languages, right? To query data, not languages in general. How does it look so far? We have two winners. Very popular questions, answers. Functional and declarative. And some of you think imperative. Okay, well, let me tell you, you can still change your mind. I see people changing their minds here. Okay. And the majority here is correct. Indeed, functional and declarative. Declarative is easy to describe. That's the difference between going to a restaurant and ordering something off the menu versus being in your kitchen and reading the recipe book and just doing the cooking, right? So declarative means you just say, this is what I would like to have as the result of my query. And the engine figures it out for you. You don't have to worry about the details. This is declarative. Imperative cannot be, because that's the opposite, right? An imperative language is when you follow a cooking book and give instructions to the computer, right? So imperative is when you talk to the computer saying, do this and do that, and then assign this to that variable, and then while this is not true, then do this and that, and so on. This is imperative. Declarative is really, give me that, like flower expressions, everything, select from where, all of that. This is declarative. Functional is technically very close and tied to declarative because the two come often together. But functional really means that you have a formal structure to the language that is based on mathematical truth, that every expression of the language returns such and such value as a mathematical truth. If you look at the structure of the language abstracted away from the syntax, so not the syntax itself, it's really just a chain of function calls, but not actual function calls. It's really in the mathematical sense, right? That every expression takes as its input the output of another expression. But of course, in a good language, you don't see the functions. You hide them under a lot of lipstick with a syntax that just looks good, right? And doesn't have any parentheses. So this is functional. All right, and a good query language is indeed functional and imperative. Low level, no, absolutely not, because you want, on the contrary, to be on the high level, hiding all of the details. And I have this other question, then why should a query language be functional and declarative? Why don't we want an imperative query language? Is it so that the queries can be parallelized? Is it so that an optimizer can make the query faster than it would have been with a literal execution of the query that you just wrote? Is it in order to delegate the details of the execution of the query to a machine rather than doing it yourself? Or is it because queries are more concise and easier to read and understand? Multiple answers possible. In other words, what do you get with SQL or JSONic that you don't get with Python? Right, let's start looking at what you're saying. Three options are quite popular. Parallel, some of you like it, but not everybody. You can change your mind. All right, so you still believe in parallelism. And in fact, that's very good because all four answers are actually correct. All of these are actually good reasons why you want your query language to be functional and declarative, right? We can parallelize. RumbleDB does exactly that. In fact, you've been already asked because you're brilliant. So even last week, you already mentioned, like, can this be done in parallel? The answer is yes. But this is not even something that you see in the syntax. It just happens hidden behind the scenes. So that an optimizer can make the query faster, yes. In fact, parallelizing is one of the many ways you can make it faster, but there are other ways. We'll talk to you about that. So that you can delegate the details, yes, absolutely, because you don't want to bother with the details of the implementation. So you just say what you need and the computer figures the rest out. And because queries are more concise and easier, this is also true. This is also a good reason to have functional and declarative languages. Which brings us right to the continuation of the lecture. I find the correct slides to share. Normally, these are the ones. Yes. All right, so we were in the middle of discovering JSONic. We're actually closer to the end than the middle. So I just have two more queries to show you, and then I'll show you how we can implement the relational algebra in JSONic, just like SQL. Everything we have in SQL, we also have in JSONic. So as a reminder, everything that comes into or out of an expression in JSONic is a sequence of items. Every expression consumes and returns sequences of items. And you see that sequences of items are a generalization of relational tables, right? What you see in the middle here with the objects is technically a relational table, but you can also have a huge mess like you see on the right here. And you can also have sequences of integers and so on, even a single item or even an empty sequence. Now, I left you here with these few examples. I told you that these flower expressions, flower, for, let, order by, where, return, they are the equivalent of select from where, right? This is exactly what it maps to in JSONic. In fact, it's the same people who designed this, the flower expressions. They're also some of the same people that are behind the SQL standard. There is just a small difference, is that in select from where, select comes first, right? So in JSONic, select comes last, and it's not called select, it's called return. But do not be distracted by that. It's only a detail. Who cares if it's called select or return, right? It's just a syntactic detail. So there is a slight difference that the select clause is at the very bottom of the query, and for corresponds to the from, right? This is kind of the equivalent. But the flower expressions generalize the select from where statements, because in select from where, it's very rigid. It has to be select from where, group by, having, order by, limit, offset, in exactly that order, right? But in JSONic, any order is fine. You have to start with for or let. You have to end with return. Everything that you have in the middle is in any order you want, as many times as you want. So you can even have a flower expression with 1,000 clauses if you want. Might be a bit slow, but except if there's an optimizer. All right, so it looks like this. And so in that case, we have this data set Git archive that from GitHub that I told you about. And what happens is that we produce this variable binding. So event gets bound in turn to every one of the billion items in there. And then we bind another variable for each one of them, which is the number of commits, right? And I get that as the size of the array. So there is an object and .payload.commits gives me an array. Then I get the size of the array. That gives me an integer that is stored for every event in here. Then we reorder based on these numbers. So this is why you are going to see it by descending number of commits. And in the output, I only keep two columns, the ID and the type, right? So you see the ID and the type. That's why the number of commits, I didn't put it in the output. I could have, but that's why you don't see it here. So you see projection and ordering, right? Let doesn't exist in SQL. That's one of the additional benefits of flower expressions. All right. Now, in SQL, we have group bys. We also have them in JSONic, as you might remember. So now I'm grouping, I'm basically trying to build a histogram, right? I want to organize all of my events, and I want to create a histogram based on the number of commits. So I'm going to create these buckets, right? Every time I have a number of commits, I put them together. How do I get the number of commits? Again, that's the size of my array. However, and this is where you see that's messy data. You might remember that this data set here might not be completely clean, right? It means that sometimes you might not have an array in here. So what happens is that if there is no payload or no commits, or if this is missing, it's okay, you get the empty sequence. It will not throw an error at you, you get an empty sequence, and the size of an empty sequence is also going to give you an empty sequence, right? And so this is a little trick, right? You can also write it more verbosely. But basically, when this is the empty sequence, what happens is that you also concatenate it with a 0 here. And when you do this filter taking the first item, that's going to just work, because imagine that there is an array, then it's going to select the first value because of that's selecting the first value. So it's going to pick this one. In case this is empty, it will just jump to the next one, because this is the empty sequence concatenated with the sequence 0, that gives you the sequence 0 with just one item. So it's kind of defining a default value, right? If this is empty, then you return 0. This is the sort of thing you cannot do with SQL, because anyway, in SQL, you need a schema, right? But in that case, we don't even need a schema, right? For who is that clear? All right, very good. So this is a very good trick in order to default to something. If there is an empty sequence, just put it whatever you want, comma the default value, and then take whichever first value comes out of this, right? Now we do something that's very common to do. We not only group by on the number of commits, we also order by them. And you see now it is nicely ascending here. And then we also put that together with the counts, right? You've already seen that in group bys. We can count max, min, sum. These are all ways you can aggregate. And now we have now for each bucket, we have the number of corresponding commits. For each number of commits, we have the number of events that have that number of commits. All right. So now I'm going to hit the stop button on the features that I'm bringing to you. I will just now look at what we've done and see how the relational algebra is implemented. So that should be a bit of an easier part. So remember, the relational algebra, it's a selection, projection, aggregation, and so on and so on. I'm going to take an example with two collections, products and stores. In order to keep things easy, in that case, I'm not going to have messy data. This is actually very clean data. In fact, you could put that in a relational table. Who could put that in relational tables? Right? It's quite straightforward, right? Three columns on the left and 2 columns on the right. And as you know, it's the same as collections of homogeneous collections of flat JSON objects. All right, so I'm going to pick this as a very simple basis of a data set with 2 JSON files, products.json and stores.json, that you can put on your hard drive or in your data lake. And so let's start with the selection. You know that the selection in SQL is not done with the select clause, but with the where clause, right? In JSONic, it's the same. It's also done with the where clause. So what happens is that you need to follow that top down, right? So there's the flow like this. So you start with the binding of P to every one of the products, one by one. And what's happening here is that you filter and only keep those for which the store is one, right? So you will keep this one, you will keep this one, and those are just thrown away, right? And so this is exactly how we do our selection. Then you return $P, and you get this, okay? So this is a selection. This is easy because it's exactly like in SQL. It's the where clause, just like in SQL. What about the projection? Well, the projection in SQL is in the select clause, so that would be in the return clause, because return is the same as select, except that since we can have messy data, we don't just say the names of the columns we want to keep, right? In SQL, we do this because we know the schema, we know the columns and so on. But since JSONix supports messy data, the way you project involves any way you want. Actually, you can project in any way you want, but one of the ways is to use the project function. It takes an object as a parameter like this, that's the first parameter, and here you specify the list of the keys of the object you want to keep, right? So that's projecting to ID and type, and you get ID and type as desired, and the third one is thrown away, the third column or the third key, all right? Can anybody tell me why we need the parentheses in here? Why did I put extra parentheses here and here instead of just $P, colon, $ID, colon, $type? $P, colon, comma, ID, comma, type. Why didn't I just write stats? Why did I put the parentheses? Yes? Exactly. So I'm repeating for those on Zoom. So you basically said we need one second argument, right? This function takes two arguments. The first argument is the object. The second argument is the columns or the keys you want to keep. So you're absolutely correct. And I want only two parameters. So you see, if I hadn't put this parenthesis, that would have been a function with three parameters, right? But that would have been an error because I need two parameters. So I group these together as a single parameter. And as you know, anything is a sequence of items, right? So I can pass a sequence of items as a single parameter like this. And now I have two parameters. All right. Perfect. What is the difference between, we have a question on Zoom. We need to wait a few seconds.
What is the difference between a return with a project and a one without?
So technically, semantically, you can put whatever you want in the return clause. It doesn't have to be project. It can be absolutely anything, right? In that case, for example, I just put $P and that's fine. So the idea of the return clause is that you have this tuple stream, right? You remember when you go down the clauses of the floor expression, you just modify the variable bindings. You just produce variable bindings. So when you arrive at the return clause, you have the variable bindings that were produced by the upper clauses right here. And what's going to happen is that for every possible variable binding coming from up there, you evaluate that expression with the values from the current binding, and you evaluate as many times as they are binding, and then you return the concatenated huge sequence of that, right? In that case, there will be one binding for every product that passes the filter. And that here, it's the identity. You just directly return the $P, right, from here. But in that case, what you do, you just don't return $P. Before that, you apply this projection. But in fact, in general, you can put whatever you want in the return clause, absolutely any expression you want, and that expression will just be evaluated for every binding. So the limit is just your imagination, right? And that is a huge difference with SQL. SQL, you're much more constrained. Here, you can return whatever you want. You can return even integers if you want. You can return a huge messy sequence with objects and arrays, whatever you want. Okay? Does it make sense?
Thank you.
Yeah, all right. Right. Again, what I'm doing here is just showing to you how to implement the relational algebra. You can do much more than that, but in particular, this is how you would implement a projection. All right, how do you order? It's with the order by. So here I order by ID and I get them nicely ordered like this. How do you group aggregation? Again, with a group by, right? So you have this grouping key, $T. You can either do it with a let followed by a group by, or if you're too lazy, we love being lazy in computer science. If you don't want a specific let, you can also directly define the variable in there, right? It's just compressing the two clauses in one. If you don't like that, just do, I don't know, let $T colon equals p.type and then group by $T, right? It would be the same thing. All right, but in any case, we group by type. And for every type, you see, here is another way to create my output. Now I create specific objects for every binding. And every time I create a key called type when I put the $T, and I create a key called num when I put the counts of $P. Remember that the magic of the group by is that all variables that are not a key, it groups them in packets, right? So for every type, you have a sequence of the products that correspond to that type. This is a sequence of products with the current type, and you just count them. This is why you get 4 TVs, 1 phone, and 2 teapots, right? For whom is that clear? All right, very good. So this you can do in SQL as well. Who could do the same in SQL? Okay, most of you. Now, how do we do joins? Now, this is new. That I haven't shown to you. Joins in SQL can be done explicitly with a join clause, but you can also do them implicitly by specifying 2 tables, and then in the where clause, you have your joining criterion, right? Well, if you just remember that, in JSONic, we are just going to have these 2 for clauses. So for every product and every store. So if we didn't do anything else, that would be the whole Cartesian product, right? That would be a huge number of variable bindings, but we only match each product to the store that it is sold in, right? So the where clause here acts as a joining criterion, right? So we are not going to have the whole Cartesian product. We are only going to have the products and the stores that are a match, right? The store of the product is the same as the ID of the store. And then for every match that we have, we return the type of product plus the country of the store, right? And that I got from the other collection. And now you see, I'm selling a TV in Switzerland, another TV in Germany, a phone in Germany, and so on and so on. And that I got with a join, because again, that came from one collection, that came from the other collection, right? And I just put them together, all right? For whom is that clear? Very good. Now you might wonder, isn't that inefficient? Because I have this huge Cartesian product, right? What if I have billions of products and millions of stores, right? That would be creating literally quadrillions, if I'm correct, quadrillions of bindings. But don't forget that this is a declarative language. So just because mathematically you would create quadrillions of items doesn't mean that physically you have them, because the engine is intelligent. It's going to figure out that it has better ways to do that. And there are very efficient ways of implementing a join. So it's not actually going to create the Cartesian product. It only exists in your mind, but not in reality. All right. And now we have cool things that SQL cannot do. For example, what if I'm going through the products and I want to list the countries in which it is sold, but that might be empty, right? It might be that some of the stores do not exist, because the data is messy and so on, which is actually what happens right there. So the way you do it is you add this allowing empty in here, and it's just going to create an empty value for $S instead of just skipping it as it would otherwise do. This is called a left outer join. This is how you do them in JSONic, right? So this is in order to allow for the case that you might have a mismatch, a lack of match on the other side. And that's what happened for this made-up product that I just called foo, assuming it is on one side, but there is no corresponding store on the other side. Okay, so this is a left outer join. Is the $$ a typo? No, it's not a typo. It is not a typo because you might remember that $, remember that this is a predicate, right? We are filtering through the stores. We only keep the store that matches the product, right? So the products coming from here store must match the store we want to keep here. $, is bound to every item in the stores one by one, right? So imagine that there are 10 stores. Then we are going to evaluate that 10 times, right? For the current value of P, I'm assuming I have a specific value of P. So I'm going to evaluate that 10 times, And every time I'm replacing the $$ by the store I'm currently testing. So I'm going to replace it 10 times, right? Every time I either get true or false out of this. If I get true, I'm going to keep it. If I get false, I'm not going to keep it, right? That's a filtering predicate. And $$ means exactly that. You can only use $$ if it is in a predicate like this, right? If you use $$ on its own, that's an error that you cannot do, right? Does it make sense?
I guess yes, but there's another question.
Yes?
Could one also use $S instead of $? Was it not possible?
So $S here comes from here. Oh, you mean here, could I use $S here? No, because $S is created by that clause, and it will only become visible after the clause, where my hand is, right here. Below my hand, you see $S, right? But this is creating $S. So that's why here it's not visible yet, right? You're creating it, okay? It's like you know, you're cooking in your kitchen and preparing a chocolate cake and you already want to eat it, but you can't because you're still preparing it, right? It's the same thing. Okay. All right. No, sir, that technically you can still do in SQL. You can still say left outer join, but this you cannot do in SQL. Because look what I'm doing here. I'm basically creating something that is not a table anymore, because now I have nestedness. I have nested arrays in there. I have lists of products. How do I do that in JSONic? Well, again, I'm using this iteration over the stores, right? And for every store, I'm going to use a let variable, not a for variable, a let variable. The let variable will find all of the products whose store matches the current store ID. So I have a specific store ID that I'm currently processing here, and I might have multiple stores that match the store ID. Maybe, sorry, multiple products, right? Maybe I have 4 products that are going to match. For example, I have in Germany, and here I have 4 products that match it. So 4 times here, I'm gonna get a true, and then I get 4 products. Do you see why I have a let now? Because the let will bind in a single shot the sequence of 4 products just once to $P, and this is why you find them right there in the same array, right? If I had used the for here, that wouldn't have created the array, it would have created more objects with only 1 product every time, which is not what we want. This is called denormalization, where basically, yeah, go ahead. So this is, the difference is, when you have 2 fors, you're creating the Cartesian product, right? So if there are multiple matches in here, that's going to create a variable binding for every single match, right? In the case of the let clause, you're still keeping together the products that match the same store. Let me give you a concrete example. Imagine that I have 4 stores and 4 products. Forget about the join criterion. I'm not going to filter anything. I'm just going to write 4. So $P in my products, $S in stores. How many bindings does that create? Four times 4, right? So 16, right? So I'm going to create 16 objects. Now, if I don't write 4 and 4, but I write 4 and let, how many bindings am I going to have now? Yeah, 4. And what happens is that then in every binding, the part that was created by the 4 contains, in that case, the single store, but the part with $P now doesn't contain just 1 product. It contains all of them, right? So now you will have in every tuple, forget about that again. So imagine there's 4 here, and we don't have that. Then what I have here is 4 variable bindings. In every one of them, there's $S bound to 1 store, but $P is bound to all 4. It's a sequence of 4 coming from there. That's what the let clause is doing, right? The let clause binds only once for every input binding. The for clause binds 1 by 1, right? That's the difference. Does it make sense? Oh, the usage of it. So in that case, we use it in order to basically create a join again. But I'm not doing it with a for clause here, with a where clause. You see, the first way of doing a join is like this. Oh, that's because of what I want to produce here. So in my output, I would like to have all of the products here for Germany, right? If I had put a 4 in there, what I would have got is Germany TV, and then below Germany phone, and then below Germany teapot, and then below Germany teapot. But let allows you to keep them together, right? Does it make sense? Yeah, awesome. For everybody else?
We have a question on Zoom.
Yes, go ahead.
Is this like a subquery versus join?
It can be seen as some sort of subquery in the sense that here I just put this here, but you can put anything else you want. So indeed, you can have, this is a way of creating subqueries in this way. Yeah. All right, yes, we have another question.
An empty sequence.
This one, yeah. Ah, let me explain that. That is a property of the object creation. Technically, if $S here does not contain that field, that produces an empty sequence. The problem is, if you remember JSON, this is a JSON object, country must be associated with one value. The empty sequence, from the perspective of JSON, is not something you can have in a JSON object, right? The sequence, they can be outside as part of JSONic, but in JSON, you must associate a key with a single value. So that must be one item in there. It cannot be 0, it cannot be 2, it has to be exactly 1. So what happens is that if you have 0 item, it's automatically converted to a null because of the object construction. If you have more than 1 item, imagine you have 2, then it's going to automatically wrap it in an array. Then it's creating an array.
There is no way that if country is associated with an empty sequence, we just exclude country. Not like now.
Oh, that you completely exclude it. Yes, the query would be a bit more complicated, but yes, you can. Yes, absolutely. You would basically create a first object with just this. Then you put an if then else around that part, right? And then there is a special construct to merge objects. Then you would merge that part with this part if it exists, right? It's just a bit more involved. It's a bit more complex, but yes, you can do it, right? Okay. All right, so that's denormalization. Now, we spent one entire week talking about types. Integers, strings, dates, binaries, and so on and so on. So we looked at all of these types. I have good news for you. Everything you've learned, the whole list, you can directly reuse in JSONic. Where should you do that? Every time you have a variable being created. So here, after the variable, you're not obliged to, but you can add a type here. You can say here it's object star, string star, and so on. I will explain what the star means. But basically, you can add the types right there. The benefit you're getting is that if the type doesn't match, you will get an error. It will tell you, right? But the nice thing is you're not obligated to do that. It's just if you want, and it's actually a very good idea if you do that. So I encourage you to do it, but you can put your types in there. So this is why I'm going to now present the types. So technically, there are 4 sequence cardinality indicators that tells you how long the sequence is. If there is nothing, it means exactly 1 item, singleton sequence. The question mark says it's either 0 or 1. So here it means either I have a sequence of 1 Boolean or the empty sequence. The plus means, what do you think? One or more, exactly. So you know regular expressions, right? So that's exactly, it's good. That's one less thing to learn, right? So plus is indeed one or more. So here it means it's a sequence of arrays, but it cannot be empty because that's one or more. And the star means a sequence of objects, possibly empty. That's the star. Again, the same as in regular. These three, actually, the question mark, the plus, and the star are the same as in regular expressions. And then you can use them whenever you want, and it will nicely check that the types are fine. So this is an example here where I have a non-empty sequence of arrays. And here I have a sequence of 2 arrays, so that's totally fine. And then I just return, in that case, I just open them. I can also have additional expressions that I haven't shown you yet. You can check if there is a specific type, getting true or false, that's instance of. That shouldn't surprise you because you have it in Java, in plenty of languages. So here you give a sequence and you ask, is it a sequence? Is it an instance of integer star? Is it true or false? False, exactly, because we have a string in there. It's not an integer, right? So that's going to give you false. Here, it checks for castability. What do I mean with that? It means you would like very much to cast this as a double, this 3.14. You would like to, but you're a bit scared that there's going to be an error. So you don't want to actually take the risk of having an error. So you just ask politely before. And the way you ask politely is castable as, and it will tell you true or false. Is that true or false? That's true because you would succeed casting. If you want to actually cast it, there is also cast as, right? All right. Another place you can use that is in functions, because yes, you can create functions in JSONic, and then you can add the types to the parameters of your function and as the result of the function, right? But the nice thing is this is all optional. You don't have to. It's fine to not specify any types. In that case, if you don't specify any type, the assumed type is item star. Item star is the topmost type you can ever have. It means a sequence of items of any size, right? So anything is anyway going to be item star. So item star is the topmost sequence type. All right. So now another way you can use the types is with JSON schemas. Remember JSON? Who remembers JSON? Schema language? Well, you can put it right there in JSONic, declare type, giving it a name as, and you put your JSON in there. And then you can use this validate expression, and this is going to validate it. So it's going to check that commit is a short. I just playfully put some random types in there. It doesn't matter. But basically, this is going to check that it's short, and this is going to check that it's a long, and it's going to basically return some validated sequence of JSON objects, right? What do you think is the underlying structure physically? Is it going to be an RDD? What do you think? Valid JSON, sequence of valid JSON objects is a... You could store it in Parquet, but why? Because it is data frames, exactly, you got it right. So this can be squeezed into a data frame, but it's invisible to you as the user. But as you might imagine, this will actually be a data frame. And since you talked to me about Parquet, I need to tell you how you store it in Parquet. And this is how you store it in Parquet. So imagine that you have a query that validates your JSON. So this is just taken from before, right? I didn't explain it again. That's an older query. But I now validate it with a schema that has 2 columns. And it succeeds. So assume it succeeds. I want to store it as Parquet. What do I do? Well, I can use my standalone jar. You didn't in the exercises, you just had it magically working in notebooks, but technically you can download the standalone jar. All you need is Java, that's it, nothing else. And then you run that with Java jar. You run the query, so this you save in some file that you call whatever you want. You have the name of the file here. And all the output you can configure that way. In that case, I'm saying where I want to output it. Overwrite, yes, because I might already have created it before and I want to override it. Only one output partition, because if I have a billion objects, it might output them in multiple files. So now I'm asking for a single file. Output format, Parquet. If you want Parquet, here I put CSV as an example, but you could put Parquet in there. And then format option, so that's for CSV. Header true is going to make sure that commits and counts will be added on the first line of the CSV file. And if you do that with CSV, then you can open it in a spreadsheet. You can continue to edit it. You can use Python visualization libraries and so on, right? So this is your interface with the real world, where you can actually save your files like that. Okay? And again, you can put Parquet, JSON, Avro, whatever you want. So it's compatible with many different formats. All right? So you can try it out if you want. To just try to download the standalone, and you can actually create. It's like a Swiss Army knife, really. You can take any format, write some query that manipulates your data, transforms it, cleans it up, and then output it as any other format. It's a Swiss Army knife of data manipulation. All right. No questions so far? Yes? Yes, absolutely, you can. Then it won't be a data frame. Let me repeat your question for those on Zoom. Then we can also use the microphone. So the question was, what if you create a schema here that wouldn't give you a data frame? Remember what I told you. Very often, the schema is compatible with creating a data frame. But I told you there's a few restrictions. It doesn't always work. One example is that you want a schema that doesn't allow for extra keys, right? You want to know all of your keys to build the data frame. If you try to create a JSON schema that is open in the sense that it will also validate objects with extra unknown keys, then you realize that that doesn't fit in a data frame, right? You can only create a data frame if you know all the keys. So in that case, that is going to validate. So the validation will succeed, but it will not be internally a data frame. And what you will get out of RumbleDB, if you try to execute that command right there, you will get some form of graceful apology. It will basically tell you, you know, I'm sorry, as much as I would like to actually store it as Parquet of CSV, I wasn't able to do it, right? That's what it's going to tell you, okay? All right. Okay, so I'm done with teaching you JSONic. You really need to spend time on it, query all you can, download the data sets, try the past exams, and so on, right? You have plenty of questions and assignments that you can work on. There is no better way than actually using it. And you will see it's very easy to learn. If you have questions, just drop them on the forum. We will answer them. All right. So it's time now that I tell you the secrets of how it's implemented, because until now it probably sounded a bit like magic, right? How can it be that it automatically detects that it can run in parallel? How can it be that it can process trillions of or quadrillions of objects? So I'm going to give you a few secrets of the internals. Many of them are actually common practice in the way that we implement database systems. Some of them are specific to denormalized data or our original research from ETH, from actually some of your previous colleagues from previous years who built that. So technically, everything starts with your query, right? Maybe you typed it in the Jupyter notebook, or maybe you saved it to a file and then used a standalone jar to open it. But basically, there is your query. At that point, your query is just text, right? This is just text. So a database querying engine will parse that text and transform it into some abstract thing that we call an abstract syntax tree. If you visited a compiler lecture, you already know that. Who knows what an abstract syntax tree is? Right? Many of you. It's some sort of abstract representation as a tree of the syntax here. It's based on the notion of context-free grammar and so on and so on. So this is the first representation we have of the query. But we're not done yet because this is still too low level. We still clean it a little bit and turn it into some expression tree. Now this is a bit more abstract and cleaner, and now this is the logic of the query we want to execute, right? Where I see my expressions, you see the count, for example, and the data flows like this, right? All the way up like this, and then you pull the string and get the results out, all right? So this is called an expression tree. It's going to ring very soon for the break. The expression tree might have inefficiencies. So there, at that point, the optimizer kicks in. It's the very smart part of the engine that finds optimizations. It's going to modify the expression tree to catch things that you might not have seen, and it's going to fix it and make it faster. I'll see you in 15 minutes, right after the break. Thank you.